Today we will start module 4, that is intractability. So in this lecture we will just introduce what are intractable problems are, and we will see there will be two classes of problems. One is called class P, another is called class NP, and what are those, right? And we will visit class P problem here, and class NP problems will be covered in the next class, right? So let us see what are intractable problems. Fine. So the problems solvable in polynomial time on a typical computer are exactly the same as the problems solvable in polynomial time on a Turing machine. So far you have seen that we have implemented various algorithms in computer, and if we had to map those algorithms to run on a Turing machine, the time consumptions are same. Still we will again cover this kind of problems in this module as well. We will prove that whatever problems we are picking up, if we just formulate it in the programmatic approach or the algorithmic approach, whatever the time complexity it is generating and whatever the time consumption it is taking, if we implement it using a Turing machine, that will be same. So these are a kind of problem which can be solvable in polynomial time. Now we have seen certain differences. Okay, this problem can be in our computer programming approach or in algorithmic approach. We have seen there are again some problems which are we cannot solve it in polynomial amount of time, and it is moving towards the exponential growth. Fine. So it is so time complexity is so high, it is approaching towards exponential growth, and it cannot be completed in polynomial amount of time, right? So again we will see how to reduce those in this module only. So in this module we will introduce the theory of intractability, that is the techniques for showing problems not to be solved in polynomial time, right? So there will be certain problems which you will see that it cannot be solved in polynomial time. That means so far we were trying to map one problem with the other, right? And we were saying that, or we were claiming that we are reducing one problem to another problem, and with the help of the previously proven problem we could conclude something, right? But if this kind of situation arises where certain problems are there which we cannot complete it or which we cannot solve it in polynomial amount of time, so our definition of reduction should change here, right? There should be some approaches in which or using which we can at least convert few problems which is having exponential growth, and if we can map that problem or reduce that problem to certain problems which are solvable in polynomial amount of time, that means we have done something, right? We have reduced the complexity of one problem by taking the help of other problem, and okay, we have proven that we have reduced the time of this problem to polynomial time, from exponential to polynomial. But remember, you will find rather I must say a great percentage, or it is enough, means there will be large amount of problems which you will fail to reduce it in this fashion, right? You cannot reduce those problems to polynomial amount of time. You cannot reduce, means apply polynomial time reductions approach there, but still we will see some problems which we can reduce. Okay, but that is not the concern of this class. In this class we will just see some problems which can be solved in polynomial amount of time. So here we are having two classes of problems. One is P class, another is NP class, right? Now here you can see if we have to define these two, P class problems are those which can be solved in polynomial amount of time by deterministic Turing machine, and NP are the classes what I was talking of, this reduction type, that if you have to reduce this exponential time consumption problems to some problems which can be solved in polynomial amount of time, so that should be implemented using NP class, because NP class does what? It just explores each and every corner, right? So each and every choices. So whenever we have to reduce some problems exponential time consuming problems to polynomial time consuming problems, we have to map it to the class of. In most of the cases it will be done with the help of non-determinism, right? So NP will be those class of problems for which we have successfully reduced from the exponential time consumption to polynomial time consumption with the help of non-deterministic Turing machine. That means these problems can be solved in polynomial time by non-deterministic Turing machine, but still there will be large amount of problems which you will never be able to map those to this polynomial time approach even by using non-deterministic Turing machine. That will fall in on another class called NP hard. We will see a very smaller portion of it in our later classes. Okay, for now just see this one. A Turing machine M is said to be of time complexity Tn or running complexity Tn, rather running time, if whenever M is given an input W of length n, M halts after making at most Tn moves. So in the perspective of Turing machine, we will say after consuming this much of after computation of this whatever Tn function is holding, it will definitely a polynomial function, and after this much of computation my Turing machine will definitely halt. I am not considering whether it is going to accept some string or not accepting, but it will come to the end, means it will halt. Okay, fine, it may accept, may not accept, we are not bothering that. We are just looking in this kind of approach that my Turing machine is going to halt or not. Okay, so let us see if my Tn is that is a function is 50 n square. You can easily guess that it is of order of n square, so it's a polynomialic growth, right? So here we can be able to say that if a language L is in class P, okay, if there is some polynomial Tn such that L equals to Lm for some deterministic Turing machine M of time complexity Tn, right? That means if you have to formally define this P class problem, it will be like this. So this language L will be in class P if this condition satisfies. That means if this language my Turing machine M can accept in this following this time complexity, means that is following the time complexity of Tn in polynomial amount of time. Okay, so directly let us move to the example now. This is a very famous algorithm for finding out minimum weight spanning tree. You know, a greedy approach is there called Kruskal algorithm. So I am not going to the details of how it works, because all of us know, we have learned it so many number of times. So what it will do, say one graph is given and it will just pick up the least weighted edge first, fine, so it will store it and then it will search for the second least cost or rather second least weighted edge. It will just merge it with the, it may get merged, may not get merged, it is not a growing one as of prims. Kruskal may come up in a disjoint form as well. So here it will pick up the second weighted edge unless and until it is forming any closed circuit. So it will keep on picking up like this until and unless all the nodes have been visited, right? So if we follow the pattern, or if we follow the algorithm of Kruskal, the famous greedy algorithm, it will be some out of spanning tree or minimum weight spanning tree following Kruskal pattern will be like this. We have marked it with heavy lines in the figure, you can see it. So this is the approach. Now let us just compute the complexity of it. So how it is going to means how it will be like, say if we having a table that gives the current component of each node. Now how we are going to proceed, we will pick up the least weighted edge, right? First edge has been picked up. Now how we are going to select the edges? By just picking up the next smallest edge and again picking up the next smallest edge. So for doing all this thing, what we are going to do, for picking up the edges or selecting edges, if we have e number of edge, total required time will be order of e, right? That is the number of edges, and finding the components of these two nodes connected by the edge, right? So Why? Because we cannot draw the edge only, right? We have to draw the vertices as well. So whenever we are picking up edge, or whenever we are searching for the edge, we are again searching for the connected vertices or connected components of it. And since we are considering there are m number of vertices and e number of edges, so choice of vertices will be done in order of m. So to do the total activity of picking up the lowest edge, it will be like order of e plus m, right? And if we have to merge all the edges, means we have picked up one, we have picked up the other, we have picked up the other in this fashion, but at the end of the day we have to merge all the edges, means we have to come to a connected graph, or rather connected tree will be spanning tree, since it will be a tree, fine. So it will, we have to come to a connected component, right? So it can be done totally in order of e multiplied by e plus m. Okay, this is a requirement, right? And if we have to find a complexity, it will be like, if we consider this total number of edges as n, and again the total number of vertices and as n, so it will be like order of n square, right? So from here you can see that it is like a polynomial growth, right? It is a polynomial growth, so this can be implemented in polynomial amount of time. Okay, but this is the general approach which we have followed so far. So we will move to Turing machine approach, and before that we will incorporate some coding pattern. Okay, so how to map this total working or this total graph using the coding pattern. So here we will have 5 symbols, namely 0, 1, the left and right parenthesis and a comma. So whenever we will write the code, we will use this 5 symbols, right? One is 0, we will use, another one is 1, another is left parenthesis, another is right parenthesis and a comma. This is the pattern for coding. Okay, we will follow this pattern. So how to assign codes, we will see that. Fine, so we will begin the code with the value of m. What is m? M's value means the number of nodes present in the graph, and the total weight limit. So what is the total weight limit? Here we will also use that one, right? Total weight limit means for now we will just consider the total weight limit as the weight of the spanning tree that we have generated. For us it is 10 plus 18 plus 12, so it is 40, right? So we will consider w equals to 40 in our case, right? So here whatever it is saying that we will begin with the value of m, then we will incorporate weight, and then we will incorporate the total graph. Whatever we are doing, everything will be in binary format. So let us begin how to code it. So if it is like this, if we are having an edge between nodes I and j, and with weight w, we will place like this I comma j comma w, but all should be in binary format. So directly move to the code which we have generated. So we were supposed to begin with what? We were supposed to begin with the number of nodes. So how many nodes are there? 4. What is the binary representation of 4? 100. So we have started with 100. Fine. So what is the weight limitation? It is 40. So if we have to represent 40 in binary, so it will be like 101,000. Done. Now we have to incorporate the edges along with the weight it is having. So how many edges are there? 1, 2, 3, 4, 5. So you can see that total 5 brackets, means opening and closing brackets, are pair of opening and closing brackets. So 5 pairs are there. So within that, first say we are storing this one, this edge from which is starting from 1 and ending at 2, and it is consisting of weight 15. So it will be like, what is the binary representation for 1? It is 1. What is the binary representation for 2? It is 1 0. That's why 1 comma 1 0. And binary representation for 15 is 4 1s. That's why 4 1s, right? Next is, if we just incorporate this one 1 and 3, so it will be 1 comma double 1, 1 for 1 and double 1 for 3, and 10 it is 1 0 1 0. So in this fashion, for other edges as well, you can easily generate the code. So this is the coding pattern which we follow to store a graph in a Turing machine, or to represent it in the Turing machine. Okay, now see, So far we have seen this one, the total complexity for Turing machine. If we just represent m and e by n, it will be somewhat like order of n square. So we have to prove that since the complexity of Kruskal algorithm is polynomial of the square, it is having n square as the time complexity. So we have to find out a Turing machine where the job can be done in this polynomial amount of time. And we will see that we will use multi-step Turing machine definitely. And again, if we have to just simulate that multi-step Turing machine using a single-step Turing machine, the time complexities definitely will be higher. But at least we can have one multi-step Turing machine where this Kruskal algorithm total working can be done in order of n square amount of time. Okay, so let us begin. So we are claiming that it can be done in, or it can be implemented in order of n square steps in case of Turing machine. So if we have to begin, it will be like we will have one tape which is used to store the nodes and their current component numbers, right? Component numbers means one node and the connected edges, because if we consider one node, then from that node where we will move, that will depend on what is the weight of the associated edges, right? In case of Kruskal, that's why we need to store this. Now since we know there will be n nodes, right? So there can be, what can be the length of the table? It will be order of n only, right? Now the second step will be, a tape can be used as we can scan the edges on the input tape to hold the currently least edge weight found among those edges that have not marked used. So we can use one separate track in the Turing machine where we can mark this one as used, mark that one as so those edges will be marked as used. We are not going to use those again, because we cannot use an edge multiple number of times. It can be used once again. So we can use input tape where there's unmarked used edges, means where the edges which has not been used can be kept, right? So that we can explore those only. So we could use a second track to mark this one, what I have told you. Now scanning the lowest weight unmarked edge takes order of n time. Why? Because total number of edges are n, so more maximum time consumption can be done in, means it can be done in order of n time. Now when an edge is selected in a round, we are placing its two nodes on a tape. Because why? Because we have to store the vertices as well. So whenever we are picking up an edge, its vertices are being stored in on a tape. Now search the table of nodes and components to find the components of these two nodes. Since we are storing the edge the nodes of a particular edge, so we can follow the table of nodes and its components to pick up, okay, if we have selected this one, what is the component of it, and we can do this. Just see, whatever the way we are approaching, whenever we are storing on the edges, whenever we are just storing the edges having which has not been used, everything, and whenever we are selecting particular vertices, and when we are trying to select the edge connected between these pair of vertices, everything can be done in order of n time, because the total number of edge and vertices, we are considering it as order of n, right? Now a tape can be used to hold two components I and j, right? So I and j means the starting edge vertex and the ending vertex, when an edge is found to connect to previously unconnected components, right? So we are connecting between them. So we can then scan the table of nodes and the components, and each node can be found each node found to be in component I has its component number changed to j, right? Means, see, just it is a how Turing machine works. So finite control will be somewhere, then it will move to somewhere else. So whenever we have one vertex, we have joined two vertices, means using an edge, that means one vertex has been traversed. Our next what is our next way out? We have to move to the next vertex, right? So the next scanned symbol is my next vertex here, that's why we have to move to there. So whatever you are doing, picking up page or traversing in any direction, everything can be done in order of n time, right? Now this is one round. Why one round? Because we have picked up one edge and can be done in this fashion. So we have to, for all the n number of edges, we have to do the same thing, right? So until and unless all the vertices are been covered, we have done it for one vertex, we will move to for the next and next. So in this way we have to move for all the n choices. So since one choice or one round can be done in order of n time, so n rounds can be completed in at most n square, right? But we know whenever we have to implement or if we have to simulate a multi-tape Turing machine using a single tape Turing machine, it whatever the time consumption in multi-tape Turing machine is, it just gets double, or not double, it just gets squared in case of the single tape Turing machine. So if now, but we have to conclude here one more thing, that we have shown that my Kruskal algorithm implementation in algorithmic approach or in programming approach, it took order of n square, and the same thing we have seen if we use a multi-tape Turing machine, it can be done in order of n square. And since we have proved that any multi-tape Turing machine can be simulated using a single tape Turing machine, just the time consumption will be squared, so it can be done using single tape Turing machine in order of n to the power 4, right? So whatever may be, so still if it is order of n to the power 4, still in case of single tape Turing machine, it can be done in polynomial time only using deterministic Turing machine, right? So this is a P class problem. So this much for this lecture. In the next we will see one what is NP class, and we will see that one problem. We'll pick up one problem and we will prove that to be NP class problem, and we will try to we will see this approach, polynomial time reduction, means if are we able to reduce this NP class, means the problems which are not solvable in polynomial amount of time using deterministic concept, can we reduce that algorithm to get reduced to polynomial time using a non-deterministic approach. Okay, that's all. Thank you.